So I gave a talk yesterday on Introduction to Monte Carlo, so we're looking forward to your talk today. Yeah, welcome everyone to day number 2 of Monte Carlo Week. Our speaker today is Dr. Micah Folsom, who's a research engineer at Intel, and he's going to talk to us about GANT4 for radiation detection simulations. Again, as per previous lectures, please use the Q&A feature. We'll keep an eye on that for you, Micah, during your talk, and we can address those questions at the end. So with that, the floor is yours.
Great. Thanks, Sean. I did see your talk yesterday, and that was a really great introduction to Monte Carlo and set me up very nicely to walk you through some GANT4 today. Yeah, so basically what we're going to do is I'll tell you a little bit about me. I realized that I think I'm the only speaker that's not currently doing nuclear things. I work in industry now doing non-nuclear things. And so I wanted to kind of give just a short one-slide overview of what I do and kind of how these things, these skills doing Monte Carlo simulations plays there. I'll explain what GANT4 is, what it's used for, how it works. It's actually, fairly challenging. There's a lot of potential content there. I'll give a little bit of detail about this, but I taught a course about GANT4 at UT Knoxville. And that was a semester where we kind of skimmed the surface of, the basics of GANT4. So you can spend a semester just getting your head around the basics and getting a basic thing running. So the question for me was, well, what do I convey in 45 minutes that will leave you with something useful to walk away from here with? So I hope that I have found the sweet spot in showing you the functionality, introducing you to the terminology and the things you need to understand to then educate yourself and to pursue more information and kind of get over that initial hurdle of where do I even look? What terms do I use? How does this stuff come together? And I'll walk through a detailed example. This is just my thesis work, but GANT4 played a very, very important role in how I approached things and what I did. So I kind of want to walk through how that all went. And I'll talk a little bit about the course and some of the resources that are available. So my background is that I did undergrad at Berkeley with Dr. Vetter. I had a lot of time with high purity germanium detectors, characterization. We have a lab that fabricates them. So I learned about all that process, strip detectors, coaxial, and all the business. At UT Knoxville, I continued some germanium work on mechanically cooled portable imagers like the ones by PHDS. And then for my PhD work, and this is really where I got into the GANT4 stuff, was designing a compact fast neutron imager using plastic scintillators. And GANT4 was perfect for this sort of work. I did some work at LBL in applied nuclear physics and Dr. Vetter's group for about 1.5 years until 2022. And then I switched to Intel. So that's where I'm at now. I'm in a group called Resolution Enhancement Technology. And there's actually a whole Wikipedia page just for this term. This is kind of the one slide summary of what we do. So chips are made with photolithography. This is a projection imaging technique, whereas in radiation detection, we tend to do detection imaging. So think of the problem in reverse. You control the source and the pattern, and now you want to, with high fidelity, reproduce that pattern on a surface. In this case, this is the wafer. And you want to do so with very, very small feature sizes. So what my group does is we solve the optical modeling problem of doing this. So the designers draw what they want. They're the electrical wizards. They know what a transistor device looks like, and they draw that. But if you make a mask out of that for photolithography and try to print that, it won't work. Everything's going to fall apart. You're going to get very poor image fidelity because of optical effects, interferences, reflections, and everything. So you need a giant and series of complicated models to understand this and to be able to reliably produce a very high contrast image in the resist on the wafer. And there is Monte Carlo modeling as part of this process, as you can imagine. It's optics, and there's many places where statistical methods and Monte Carlo specifically are very useful. And to kind of drive the point home, Up on the top right here is kind of the main technology now that we use to print chips. It's 193 nanometers wavelength. But the next generation, the stuff that is starting to be used now is a lower wavelength, EUV is what we call it. And this is what the scanners look like. There's an enormous number of mirrors and scatters and things that you're doing, but you still need to maintain that same image fidelity. And so again, it's a very complex modeling and engineering problem to kind of get around this. So this is what I'm working on now, kind of high level. And a lot of the skills that I've learned in the nuclear space have been useful in understanding and tackling this sort of problem. Okay, so with that behind us, by the end of today, I'm hoping that you have a high level understanding of Geant4 and what it can do and how it works. Be aware of kind of some of the high level differences with MCMP and be aware of the resources available to learn. This is actually, I think, one of the most critical to me. You should, after this, if you wanted to be able to go find the information you need to put together a basic Geant4 simulation. And having the confidence to be able to do so. And I make that point because this is an infamously difficult piece of software to learn. I've encountered a lot of students over the course of my education and career, and other researchers, that if you don't have a C++ background, if you don't have a lot of experience working on the command line, doing things like that, this can be a very scary task because you end up having to learn like 3 complicated things all at once. And so I think it's important that we have better resources and kind of a clearer pathway for engineers to do scientific research and use this tool without kind of getting bogged down in all these details. And then, of course, as a disclaimer, I'm only speaking on behalf of myself today. I'm not representing Intel or any institution or anything. This is just my experiences and stuff that I've worked on. Okay, so Geant4, it stands for geometry and tracking. Some people say Geant. You can maybe make a case for Geants. Doesn't really matter. Do what you like. This is developed by CERN, the high energy physics people, the Large Hadron Collider people, for real big scale terabyte, petabyte, kind of data experiments. Many particles and interactions and stuff going on. So this is actually overkill in some sense for our purposes, right? We're doing, for the most part, relatively simple neutron, gamma. It interacts with the material, things happen, and we want to extract a signal. But very nice for our use case. So this is actually fairly old, 1974. So before a lot of us, well before a lot of us were born, this was a Fortran tool, and they released it as a C++ tool in the 90s. It is closely associated with Root, if you're familiar with that. A lot of the developers are the same. There's a bunch of overlap. Geant4 kind of supports Root natively for doing I/O stuff, if you want to go down that rabbit hole. It's open source and it's very customizable. That's been one of kind of like the key points, is that you can do anything and everything if you are so motivated in Geant4. I think of it as a very literal approach. It's object oriented, and once you kind of look into the code and what they're doing, you're like, oh, yeah, this is how you do this. You have a particle object, and this has a position attribute and a momentum and an energy, and it's got all the particle attributes, and depending on which particle you are, you inherit the base stuff, and then you add your things. Maybe you have mass, whereas some things don't, and so then there's a whole hierarchy there, and it's fairly easy to understand. You have a G4 gamma object, and well, that represents a gamma ray, and that has all the attributes that you'd expect from a physics standpoint. So it's fairly intuitive in my experience. It's not used for like reactor calculations. It's very inefficient for that purpose. You can use it for shielding stuff. There's a few extra kind of things you need to do for that. But it's really great for a lot of our application space, which is radiation detector modeling, kind of evaluating designs, understanding what's going on, efficiencies, and how will our algorithms perform on the data. But as I mentioned, again, it's very difficult to get started with. C++ is a hard language. It just is. It's not easy. There's a lot of pitfalls. It's low level and it's high level. It's got a lot of high level abstractions that are actually really computer sciencey, and you have to spend a lot of time getting your head around it, but you also have to understand pointers and memory addresses and all this other stuff. And it just gets really tricky. The tooling around it, compilers, the build systems, also not friendly. CMake makefiles, it's a real headache to learn. And then you have to understand like Geant4 and physics and like the thing that you're actually trying to do. So there's a lot of hurdles here. And again, if you don't have the background, it seems like a huge task, and it can take months to get something sensible going. So for us, for nuclear security applications, we're really using a small subset of the capabilities of the tool. Gammas, neutrons, maybe you have a muon idea and you're trying to look at a cask, or other particles, or there's other stuff, but that's all in there because it's the high energy physics community, so they've encountered this already. Radioactive sources, generated particles, DT generator, whatever neutron source you can kind of think of, can do that. Materials wise, again, basically covers everything that we encounter: semiconductors, scintillators, different flavors of those. If you have a totally new category of material you want to check, there's probably a pathway, or it's already built in, because again, detectors are the name of the game in high energy physics. So it's really good for the questions that we ask, which is, how do we build like a new design, a higher resolution image, or a more efficient detector? I want to kind of iterate in the design space and look for a new opportunity. So a really great tool for that. So okay, compared to MCMP, this is the one-slide summary. I'll caveat that I am not an MCMP expert. I think the last time I used it was 2014 or 2015 for a class for kind of one project. So I'll leave that to the talk for tomorrow. But kind of high level, open versus closed source, there's trade-offs to this. MCMP is out of the box, it'll work, and you can set up an input deck, which is really just a config file. You're not writing code, you're kind of specifying configuration. So there's way fewer places where you can screw up. Debugging is kind of a lot easier because the tool will read your configuration, and if you give it an invalid something, it'll generally give you some feedback to that effect. The drawback of that is that you can't look inside and see what it's doing. If I have a question about Geant4 and how it's doing it, I can look at the code. I can just go into the class and I can see the function. I can follow the thread and say, oh, it's doing this loop and it's changing this attribute in this way. And that's now unambiguous what is happening. I didn't have to email someone and wait a week for a reply or whatever. If you get stuck, you can't solve it yourself. The forums, you can. I mentioned that the two founders, if you post in the forums, sometimes you might get a reply from one of the OGs, which is kind of funny. Very, very helpful community. And of course, things are shareable if it's open source. It's a lot easier to kind of give someone from even another country, my Geant4 code, and I don't have to worry about export control or things like that. So Geant4, C++, a lot of people don't know that there are actually fairly fleshed out Python bindings for Geant4. And so if I were actually going to make a recommendation today, that's what I would say you should use. I haven't used it extensively myself. I only really learned it existed like a few years ago in like a real way, but I know that people use this at a real scale, and it works. So why mess with C++ when you can just do some Python? And that may be easier for some folks than learning how to write an MCMP input deck. The learning curve is kind of a wash. I feel like it's hard on both sides. Licensing is obviously a bit easier on the Geant4 side. Physics customizability is also another really big thing with Geant4. I can select or customize, specify whatever physics I want. I can make new physics. If I have a very specific, I got a new material and the current physics in Geant4 doesn't have processes for modeling that, that's fine. I can write the code and I can make it myself. Geant4 is also very good with optics. There's a lot of capability to do optics. Visualization, I'm not super familiar with an MCMP, but in Geant4, quite strong. I can simulate individual tracks and watch them bounce around in the visualization in real time, and it's very great feedback as I'm trying to develop my stuff. Open geometry specs, being able to take a CAD file and turn it into an input for Geant4 is also a thing that's possible and cool. And again, Python. So where is it used? All over the place. Energy physics, space. There's a lot of patents. I found this is actually from a May 2024 paper, these two figures. Geant4 is used a lot for Monte Carlo modeling compared to the alternatives. It's been developed for a long time. It's trusted, it's validated, and it's got a large community. So this is it's a tool that's got a lot of backing. And so this is a good reason to use it. Resources. So this is important if you really want to learn. This has been famously one of the hard things and one of the limited things about GF4 is that the actual learning, the kind of the best way to learn has been almost to go to a conference and do like a week-long workshop where someone sits with you with your laptop, you get GF4 installed, and you do a crash course that's 4 hours a day or something, and you put together some GF4 examples. It's just the online resources are limited. The number one document, you'll refer to this over and over again. If I have a question and I want to understand, this is the first place that I go to. It's the application developer's guide. As a user of Geant4, you're developing a Geant4 application. And so this document is like 900 pages and it's got everything. It talks about how everything works. How does a track work? How does a step work? What is an event? Stuff that I'm going to go over here. This is required reading if you plan on using Geant4. And to kind of drive this point home on the top left right, this is what they show in the manuals, the simplest example of the main function, which is the entry point in a C++ program. And this is the absolute simplest. And you see how long it is and how much boilerplate you're writing. And it's actually obscuring several things, which each one of these lines requires two separate files to define these objects. And so you've got probably 50 to 100 lines of code in the trivial, this is the simplest example. And so again, that's a lot for a trivial example, right? And that kind of, again, lends to the difficulty in getting running with Geant4. But to understand, again, how things work, you'll want to start here. The Doxygen documentation is the next thing. It's essentially an automated, it's a tool that looks at the code and then makes an HTML clickable. You can click through the code essentially in a browser. And this is really useful. You can search for things. And if they've written documentation, which they haven't in a lot of places, it will grab that and show it to you in the website. So that can be really useful for quickly looking things up without actually diving fully into the source code. And then, of course, if you need to do that, go to the GitHub, go to the Geant4 project, you can search, and you can find what you're looking for. Kind of the last resort. Okay, so that's kind of it for resources. If you want to learn, start there, and I have a few more things later on as well related to the course. Okay, so getting into how does Geant4 work? What are the terms that we need to understand in the run? Again, Sean did a really nice job of setting up how kind of Monte Carlo works. You're mostly iteratively going through and flipping a coin and making decisions and saying, what is happening to this particle based on the physics and the probabilities of the various reactions that are possible. In Geant4, the way this works is starting kind of from the top, you have a run. And a run is just a collection of n events. And this is easily parallelizable if you want to run on 4 threads. You can tell that to Geant4 and it'll create 4 run objects with n events. And now you're running 4 times as many in 4 separate threads, and you're roughly seeing a 4x performance benefit. So just a collection of events. An event is one or more particles produced by the source, all of their secondaries and all of their offspring and all of their tracks. So that's kind of everything. A particle is born, it does its thing, it produces all of its secondary, tertiary particles, all the tracks and steps associated with those, and those are kind of collected into one event. And Geant4 is just making a bunch of events, randomly picking, the starting energy or direction or whatever of the initial particles. The track is then the series of steps. It's a full list. You can think of an array. It's just a set of steps taken by a particle on its journey. And then a step is a start and end position. So step is 2 pieces of information. It's where you started and where you ended. It's a line segment defining the movement of the particle in that iteration of the simulation. Then you've got the primary vertex. This is the terminology Geant4 loves to use. And this is just the starting position and properties of your particle, the things that makes it go. So that's going to be what they call the momentum direction. You can think for a neutron, you're going to think of it one way. For a photon, you're going to think of it another way. It's kind of easy to summarize that as just the momentum direction. And of course, for anything to happen, right, you need some possibility, some starting push or some starting energy so that the particle is moving, or you have to start with like a radioactive source. It's got a decay time, and GN4 can kind of fake and say, all right, after this amount of time, particle decays, and then a particle is released with this initial starting position, momentum, et cetera, based on the libraries and the properties of that decay. So generally, we're assuming in our simulation space, static conditions, things aren't moving. You want to fake movement, you need to do multiple simulations and move your detectors around or move your source around. And then the particle histories are all independent. So each event is totally separate, and that's why the parallelization works. You can just, n events, it doesn't matter where, how you do them, they're all totally independent and don't affect each other. A decay now doesn't affect a decay later. And the process is then you generate your particles, you step them until they are absorbed, they stopped, so nothing can happen to them, or they've left your geometry. So as a developer, you're actually writing a C++ or Python application that invokes the Geant4 libraries. You don't touch the top part, the Geant4 run manager. You don't define anything. You don't override anything. You interact with it and you tell it, here is my stuff. Here's my geometry. Here's my physics. Here's my custom actions. And you give it to it. And that's your hook into the program so that Geant4 will call your functions and not the built-in ones. And so there's kind of three things you have to provide in general. You need a geometry, right? Won't be able to do anything without a simulation space. You need some physics. You have to tell, there's an enormous amount of physics you could define. So you have to tell Geant4, what am I doing? What is allowed? What processes are happening? What particles exist? And then you have to give it a source. Where are the particles coming from? Where's the action starting in your simulation? Geometry is 100% on you. You have to do something. There are good stock physics lists, and I have a slide for that, that are just fine for using for getting started. And then there's also pretty good stock built-in particle sources, again, that will do monoenergetic or spectra or things like that, of different shapes and distributions to cover a lot of the basic use cases. And so the colors here are highlighting user kind of defined classes in pink. And then the hook functions in yellow. And what happens is you override Geant4's construct function. Instead of calling its construct function, it calls your code, and then your stuff happens. And that's kind of the general theme for how this all works. There is a handful of manager classes. They're single global instances. They're called singletons in C++. And this kind of is an easy way to do high-level control. I can just, anywhere in the code, I can say, hey, give me the run manager, and then do stuff. And that's, you can make arguments about the cleanness of the code and whether that's a good strategy, but it's very easy to work with. And then they provide you hooks via inheritance. I'm not going to go into polymorphism in C++, but you're overriding their objects. You're superseding their functions. And so they say, we have a declaration that this function must exist. It must be called construct, and it must have this form. And then we come in and override that and say, OK, we follow that template. And then it calls our version instead of their version. And that's how a lot of stuff works in Geant4. OK, so the geometry. There's three pieces to this. There's the shape. There's the logical volume, which is just the material. And then there's the physical volume, which is the placement, the rotation, and the copies. And again, this is made kind of modular and programmatic so that you can imagine for Atlas or something, they have many, many placements of the same detector. And you don't want to code up each one individually. So there's a very easy way to do copies of the same volume. They connect. And you can see in the code here, you essentially start with the G4 box, the solid. You pass that in when you make the logical volume. And then when you make the placement, you pass in the logical volume, or sorry, the logical volume here. And so it's this kind of chaining thing where you define the shape, you define the material, and then you define the placement, and you're kind of passing them one to the other as you go. And then you're also stacking them. And this is like MCMP, where you need to nest your objects. Things are inside of other things. You have an outermost simulation world volume, and then everything is inside of that. And the positions of the things inside are relative to the origin of their parent object. And so here in the code, you see it's passing the world logical volume into the detector placement. And that's saying this detector is inside of this object. Um, Again, the special world object, it doesn't have a parent. You pass null in for its parent. And Geon4 recognizes that if you do this for multiple things, it will crash and yell at you. You cannot have multiple world volumes. It covers all of the shapes you want. It'll do binary shapes as Boolean operations. So if you want to or and find the intersection, you can do that, certainly. And again, I just want to emphasize, you want to stack things. You can kind of, because you're writing the code defining the objects, you could do this two ways. If you, for example, want to define a cylinder, a tin cylinder, it's got like a millimeter wall and it's filled with air. You could define a cylinder with an outer and inner diameter that defines a 1 millimeter wall, and then I could have a thin cylinder, so that's a shell, and then I have a fully filled air cylinder inside. But now I've kind of created a boundary problem. If I've done some math to create the numbers that are determining the inner and outer diameter and for the cylinders, I might run into a floating point thing, and now I've created like a infinitesimally small gap between the surfaces, right? When you nest them, no problem. I define a fully solid tin cylinder, and then I put a fully solid air cylinder inside of it. And however big that air cylinder is will define the boundary between the two. And now there's no problem, right? So you deal with the floating point gotcha, and there's also a bunch of performance hierarchy crawling computer sciencey stuff that this has advantages in. So just so you see, there's a huge number of geometries. Pretty much everything you need is in here, including surfaces, if you just need to do a surface. And then the last bit about geometry is just collecting information. It's tied to this just by design. You can define what's called a sensitive detector in the terminology. And this is essentially a volume that you care about hits. You care about interactions happening. You want to collect information about the tracks and the steps and the particles that went through this volume and deposited energy or did other things. This is kind of the official way to do that. And it's fast. You can use filters. I can say, I only want these particles. I only want these energies, et cetera, et cetera. Things going in this direction and all that. And so this is kind of it's more detailed. It takes more setup, more boilerplate, but you get all of the information: the track ID, the parent ID, if it's a secondary, which volume it's in, what type of particle, what type of process created it, Compton, photoelectric, things like that. So this is kind of how I've seen kind of when everyone's collecting tracks for real and they want all of the information, this is kind of how you do it. Okay, so a note about particle sources. You can define your own. I mentioned that there's a pretty good stock one that I recommend starting with. Most cases, it seems like a lot of people do end up defining their own, but I will put in a word of caution here that if you're going to do this, you should test. You should test aggressively and thoroughly, and you should make absolutely certain that you're getting the behavior that you want. And the reason I say this is because there's a very common pitfall. So the situation is that you want to sample, so you want to create an isotropic particle source. And that means creating on a sphere uniformly, you want to uniformly sample a sphere in direction space, basically, right? In theta phi, you want to uniformly sample every direction. So you might naively think, well, that's fine. I will uniformly sample theta and phi over their respective domains. And that's this picture on the top here. And then I will calculate x, y, z, and then I'll make a normalized vector that has, the distribution. So you sample theta phi, and you get this picture, and you go, great. It's uniformly sampling. If you project that onto the sphere, you'll see clumps around the poles because the theta phi angles are more dense at the poles than they are at the equator of a sphere. And now you've introduced a really nasty and subtle bias into your particle source. And this, you may not understand this or see this, and you may get weird results in your final thing and be like, why is my efficiency, like, what is going on here? And it's this sort of thing can be really a scary and unfun bug to have to figure out. So again, if you're gonna do your own thing and define your own source, make sure to test it, validate it, and really convince yourself that it is doing what you expect it to and everything. Same with anything really in the code. Geon4 gives you a lot of power. So that means there's a lot of opportunity. Okay, so physics lists. This is something you'll have to define. And again, Geon4, it's high energy physics. There's a lot of stock stuff that's already here for you. every real big size project I've worked on has ended up defining their own. They kind of take a stock one and they say, well, we want this Livermore, like this, EM process, we want the Livermore data instead of whatever they're using for the default. So like, there's different origins or sources for the data that feed these models. And sometimes some of them agree better with our experiments than others, and you just learn through experience which ones those are, and you kind of learn to use those. So I've highlighted here for our nuclear security, gammas and neutrons of the energies we care about space. This is where you're looking when you look at physics, the built-in physics list in Geant4. So these two, the BERT and the HP, are the kind of categories that we are going to include the physics that we care about generally. You'll see this QGSP BERT. So this is if you're just doing like gammas and X-rays and stuff, this is fine. This will work just fine. It's used by Atlas. It's good enough for them. It's good enough for you. Standard EM processes, you're going to get photoelectric and Compton and all the usual things. And if you want to do some neutrons, again, low energies up to 20 MeV, which covers most of our cases, then you add the _HP to this, and you'll get both the EM gammas and X-rays, and then also the neutrons. So yeah, this is nice. You can kind of grab, and these are totally, again, for getting started, very, very acceptable for going. There are these BIC versions. These are made specifically for shielding calculations. I forget exactly what the optimization is there, but if you're looking at doing that sort of thing, take a look at those. Oh, and I will note that this is extremely powerful. I can't stress enough, when you can turn off individual physics, it really helps build your understanding of the physics of what's going on, and it helps you build your confidence of what you're seeing in your simulation. So I can look at the outputs and say, oh, I think that this little peak in the spectrum is from this process, but I'd like to know that for sure. And this is an easy way to do that. You can just turn off the physics, and then if you don't see that peak, well, you've got your answer. So again, it's really nice to be able to select like that and to customize. The user interactivity I also found really useful. We don't think about UI, making UIs a lot. We're kind of more engrossed in doing the science, but in my application, I needed to iterate over detector geometries a lot and change them around, and it was really helpful to be able to see them, to shoot particles around and convince myself that I was doing what I thought I was doing in the code. So for debugging, this is just fantastic. And you can generate particles, you can shoot them around. And you see kind of here a lot of this is stock. This is built in, comes with it out of the box. You can also set up macro files that will enter the commands. And again, if you want to iterate on things, you want to change the source, you want to change the geometry, I can just set up a bunch of macros that call commands that do those things instead of changing the code, recompiling, and running again, which is the worst way to develop. It's hard to track, and it's very tedious and time consuming. You want to run a script with your code, and then you're just you're turning the knobs with your configuration, right? And so this is how to use it, and this allows you to really rapidly iterate and prototype things. So then getting your data, you do all these things. You define your physics list, your geometry, your particle source. You throw all this together, and you've got an application now that is doing a simulation. Great. You need to get the data out. And in MCMP, you'd be using tallies. There is this functionality in Geant4, but it's newer, and I say newer. Last 5 years, this has become featured more prominently in the examples. But you can functionally do the same thing. If I want to collect all the energy absorptions in a volume, there's a pathway to do that, and they show you in the examples how to do that sort of thing. You can output it to CSV, HDF5, or root file, your own binary, whatever you want to do there. There's a bunch of built-in stuff, or you can just define your own. So you can take a look at this. Writing is kind of a pain point. I don't love how this has been in Geant4. It's always been kind of difficult and not particularly fun to sort out. But a lot of physicists kind of are happy rolling their own thing because they're working with high quantities of data. Yeah, if you're just doing simple stuff, just writing histograms, you can write text files. That's easy to consume. If you're writing tracks and the full histories of particles, you're going to want a binary format, preferably something compressed like HDF5 or root, so that you're not taking up enormous amounts of disk space. And I'll once again stress, because you're writing all of the code, you have a lot of opportunities to make mistakes and introduce subtle bugs and biases. You're killing particles, maybe you're counting things wrong, or just good old-fashioned, bugs. And so it's very important that you test your code and sanity check it, run small numbers of events, look at the full histories and make sure that they make sense, run variations on your simulation and make sure that it's perturbed in ways that you understand, and do it as you add things, as you develop with each little piece so that you're not trying to untangle a lot of things at once. Really just good general software development practices are important here. Okay, so I realize I'm running fairly short on time. I'm going to very quickly go through how I use GeoInt4 for my thesis work. This was a fast neutron scatter camera effort. We had a collaboration where we were looking at different designs, very fundamentally different designs, to accomplish the same thing. And so what we wanted was one GeoInt4 simulation where we could do these very different designs, maybe the same photodetectors, the same SIPMs with the same multi-unit PMTs, but the volume's chopped up differently. Maybe you have some different reflectors and things in there. And we want to be able to enter one command and you just flip between the geometries and then you define the same sources, the same everything, and then we're all sharing the benefits of the same code. We're all testing it and all that sort of goodness. So that was kind of our task. Inside of this, I was tasked with one of the approaches, which was using coded aperture inside the scintillator to image the scintillation light. So I'm not using coded aperture to image the incident radiation, the neutrons. It's localizing the neutron's hit location inside the detector, which is kind of a weird idea, but I had a lot of off-the-wall geometries and detector designs that I wanted to try. So I was able to do this in GeoInt4. I defined functions to build these detectors and then was able to flip between them easily and collect all the tracks and events and feed that into our imaging algorithms and evaluate which one is performing best, what sort of resolution are we getting in light, photo detection efficiencies, things like that. And this was the design I settled on. So it's kind of this plate or slab thing where you've got stacks of these plastic scintillators. You've got the coated mask down here in purple, and then you've got photodetectors at the bottom. So you're capturing the pattern cast by the shadow cast by the light, the scintillation light through the coated mask, and then you can use that to determine the hit location. And GeoInt4, it looks something like this. A neutron comes in, produces hundreds of scintillation photons that bounce around in the slab and make their way down to the phototube. It hits another slab, it scatters and hits another one, makes another energy deposition. Same thing happens. You localize it within these slabs, and then you've got your two positions and energies for your neutron, your fast neutron imaging back projection. We use Californium. It was a custom source. Sean talked yesterday about PDFs and CDFs. We did the exact same thing, for defining the source here. Look at the literature. There's a split of gammas and neutrons you need, like the ratio and energies. That's kind of complicated for Californium, so we just coded it up, and we had a custom source that we were confident in. So then I built this detector. I simulated it. I came up with a design that we thought was optimal in the parameter space. We needed to build it, and that meant understanding the detector response. So an event occurs at some location in the detector volume. What is the PMT see in position and time space? That is the response in our case. And so I used GeoInt4 to simulate that and map that out, understand it. But then past that, when I built the detector, I also used it to fit, and I interpolated on my simulated response where I inserted, I fit that to experimental data. I used a collimated beam. And I poked, I perturbed my detector at discrete points, saw what the response was, and I fit my simulated data to that and interpolated on that to get my event reconstruction. So again, GeoInt4 incredibly powerful here for me being able to build a functional, real detector that actually was able to localize events. And this is what that looks like high level. I have a simulated spectrum. I have a space where I'm blurring and scaling the simulated result to match the measured experimental spectrum for this collimated beam source. And then I can interpolate on that grade. And this 3D view is the real beam data reconstructed in 5 discrete slabs using this fully assembled detector. The very bottom, this is the back projected neutron image. And the left thing is the experimental result. I see this, right? I put all my things together and then I make this and I'm like, okay, if I squint, simple back projection, no MLEM. If I squint, I can convince myself that I'm doing this. But I want to simulate what I would see for a source in the same position and then run my algorithms and see, yes, the point source is really here. And this really is approximating what I should see. Again, Geant4 providing me a really nice sanity check that my experimental data made sense, and I was seeing what I would expect to see based on the model. Okay, so that's kind of it for the actual Geant4. Hopefully that was enough, the right level of an overview, without showing the details of the code and all the classes and stuff, kind of how things work and how things come together, what the key pieces are. If you really are interested in learning Geant4, you have a use case. Again, the online resources were kind of rough. Definitely sign up for a class at a conference if you can. But I also taught the course virtually at UTK. Everything is online. The students submitted all their assignments on GitHub. Made heavy use of GitHub. So this is all open to the public. You can go download the lecture slides. You can see the codes that I used for the demos. And you can see the assignments and everything. The only thing you won't have are the videos, unfortunately, but everything else is up there. And essentially, I go through and do a crash course in C++ and kind of get you familiar with how does this work on a basic level, enough to write some code. Writing a simple 1D Monte Carlo just from scratch. It's a very fun little back of the envelope, simple project to just say I have a 1D track, I have a particle, and there's like one or two processes. It can die, it can skip, it can scatter, it can skip a few steps or something. And then you can make nice little histograms and spectra of where all the particles died. You can fit them and convince yourself that, oh yeah, that exponential has the constant that is defined by the probability that I inserted in my simulation and things like that. And then getting into Geant4 examples, modifying them and kind of writing our own bigger Geant4 code from scratch. And then the students got to choose their own final projects. So this is the list of things they did. Multiple scatter simulators for measuring particle lifetimes in flight, fusion, looking at the what's coming out of a fusion system, looking at the neutrons, some shielding sensitivity analysis, distributed sensor radiation detectors for looking at a source moving at a kind of city scale, molten salt reactors. So I said that it wasn't good for doing reactor analysis. If you treat your whole reactor volume as a source term, well, it's just particles coming out of the source. And then you don't need to model the full reactor. You can start there, use another code to do your reactor analysis, and then take the flux or the profile coming out, and then put that into Geant4 and start there for your detection simulations. Of course, neutron gamma imaging is always going to be popular, and then some time of flight measurements, things like that. So I'm thinking about doing this course again in the future, and I think if I do it again, I'm going to do it in Python. I think it'll be a lot more accessible in the Python Geant4, just so that it's a lot easier and we can skip the whole C++ crash course. So here's the links and the resources, the Geant4 Python. There's a few projects, so make sure to use the latest, most up-to-date one. This one, it's not 100% one-to-one with the Geant4 C++ API, but for our purposes, it covers virtually everything that you'd need to get started. If you want to use the C++, either because you're just interested and you want to learn C++, or you already know it, or you're working in a context where they already have a Geant4 simulation and you are going to piggyback on that, again, go check out the class, and this will maybe give you a good starting place to get going. And of course, read the application developer's guide. Read it again, and that's it. So I'm a few minutes over, but thank you. And
Yeah, thanks, Micah. That was a great lecture. I've only used Geant4 a little bit. I took one of the courses and I did learn quite a bit, but I did find the C++ piece quite a bit of a hurdle for me personally. So I definitely resonate with what you were saying there. There are a few questions in the Q&A. You should be able to see it if you click at the bottom of your Zoom window there.
So bottom or top? Oh, Q&A. Okay, see. Yep.
Wherever the toolbar went. Yeah.
Yeah. Okay. All right, yeah, I'll just go through these. So GM4 being a Monte Carlo simulation toolkit also includes standard nuclear data as libraries. Yep. While publishing, GM4 simulations are always taken with a grain of salt, even when validated. I don't know if that's true. I think they're pretty heavily validated, and you can see even, I did my thesis work, and you could see that the simulation matched reasonably well with our experimental data. You can use the libraries, of course, are very, very heavily validated that GM4 is using. You can use your own. If you want to use NDEF explicitly, you can just do that. If you don't trust the GM4 libraries, then go ahead and plug in NDEF and use that. So up to you. But I would say it's pretty widely, as I showed with the picture for the adoption and the citations, it's very heavily used in radiation modeling. Both by high energy physicists, medical space, et cetera. Okay, so the next one, how effective is it in describing nuclear fission? Yeah, so I haven't used it for fission. I think it'll do spontaneous fission. I believe that's built in. If you're trying to simulate, a bunch of neutron-induced fissions, I believe that also is in there. I mean, the cross sections are there, and I vaguely recalling a graduate student friend that did use GM4 to do that sort of work. So I would say, yes, that is in there and possible. And if you want to do that, you can do that. What are common symptoms later on that our particle sources are biased? Well, you'll see biases in the results. So that's usually your first sign, is that you expect a uniform or flat response. And I again, for part of your testing and validation, I really encourage you to do this exercise. Even if your detector geometry that you're really testing isn't normally flat, maybe put in a flat one and see that you get the shape, the flat response that you expect from a flat source, or things like that. You want to sanity check that, and you want to look for these sorts of things in your results where you expect it to look a certain way and it looks a different way, and you really want to dig into why that is and understand it. All right, so can someone who's used simulation MCMP easily get it? I think so. Once you have your head around Monte Carlo, that is a really big step. The geometry definitions, I think, are intuitively similar in terms of your nesting geometries and maybe taking unions or ands, kind of Boolean ands of geometries. I think that's, yeah, fairly intuitive. The real hard part is kind of everything around it, is compiling a code and collecting the results and doing the file IO. And you have to now think about this. And whereas MCMP just does this for you, it just writes the tallies out to the output file and you just look at it. And so that's, I think, the part that will be harder to get around. Design patterns. I'm not sure which kind of things exactly you're thinking. It's C++, it's object-oriented. I mentioned singletons as like a thing that they use that people might debate about. You don't have to worry too much about the memory management, for example. For a lot of the stuff, they do handle most of the things for you because you're kind of overriding their objects. So they've already got an instance. You just need to override the functionality, if that makes sense. So then the next question, does not implement lattice structure. So I don't know. I'm not aware of any lattice structure stuff in GM4, so I would say that's probably accurate. If you wanted to do that sort of analysis, you might want to use a different code. Yeah, I would have to think about that. You might want to look around. It's possible. I'm sure people have thought about it. What can GM4 not do? And then elaborating on how to test. So because you're writing the code, that's a hard question to answer. The sky in your imagination is really the limit. They provide a bunch of hooks, and you might be limited in how you can interface and define things. But at some point, you have the code. You could change GM4 itself if you wanted to, right? If GM4 is limited in its capability, you can submit a pull request online, and you can say, hey, you can't do this. I need to do this for physics reasons. And then maybe they add that to GM4. And so, yeah, the sky really is the limit, and it's really up to what you can code up. That's kind of the limit. And then on how to test. So again, it's a lot of kind of general software engineering kind of best practice stuff. Do small changes and then test those changes in different ways. Test the edge cases. Give it inputs, give it geometries, give it source configurations that will expose weaknesses in your logic. That's how you kind of do any sort of testing, is give it cases that are going to stress your implementation and look for holes. And that's what you want to do. If you want to look for your source not giving you the profile that you expect, and you want to set up tests to that effect. Okay, so among MCMP codes or the Monte Carlo codes, I wouldn't say better. It's, there's different levels of adoption. The best solution is the one that you can use. Right? It's the one that will solve your problem. And if you're in a space where Scale or Fuka or another Monte Carlo code is immediately available and directly relevant, or you've already got infrastructure for that code, then just use that. There's no reason to adopt a whole new framework to do a thing when you've already got a lot of effort on something. So yeah, it's just whatever is the appropriate tool for the application. There are many softwares that work on top of Jamf4. Yes, those are great. Gate is another one for medical, is a pretty popular example. Yeah, Jamf4 is a great base to start with. And if you have a more specific application, like you want to do PET, and you know that you're going to be simulating these geometries. It's detectors in a ring around an object, and you're working in that space. You want to create a lot of facilities to make defining those geometries really easy, which Jamf4 doesn't. You're defining just you would define those from scratch normally. So Gate has facilities for, say, I want a PET system, and it's got this inner, size, and the detectors look like this, and then it just places them all for you. So those are fantastic. Those will save you a lot of time. People have already developed, the high-level abstractions so that you can not worry about mathing out the detector placement. You can say, I want this placement, I want this source, do it. And now you're good. Those are great. Computational speed, CPU requirements. I think they're all comparable. Everyone thinks about this when they design these codes. There's a lot of performance optimization in Jamf4. It's pre-allocating objects so that in large batch operations, which is a lot more efficient than allocating individual particles as you need them. And doing the parallelization is fairly easy in Jamf4. So yeah, I would say it's comparable. Is it feasible to integrate machine learning? Again, sky's the limit. I haven't looked at that for what's already there, what the community is kind of integrated. I would be surprised if there isn't kind of facilities that are starting to exist in the open source project for that sort of thing. And again, these are high-energy physicists that are working with huge amounts of data and hugely complex reaction chains and stuff. So machine learning for them is arguably even more useful or important in this context. So yeah, I would take a look. I haven't looked around personally too much, but I would be a little bit surprised if that's not there. Running advanced examples does seem to require a coding system. Yeah, things escalate quickly. The learning curve is steep on Jamf4. Absolutely. So. Try to start simple and do a piece at a time and kind of just build up your understanding is my best advice there. Plasmas I believe so. Don't quote me on that. I think it should. I think you can define the material parameters to include that, but I would take a look if you need that at the material definitions. Okay, yeah, papers using Jamf4 to estimate absolute efficiency. Yeah, absolute numbers, those are tough. Those are real hard. Can we use the output of such a simulation to integrate commercially available composers? Yeah, like Genie 2000. Yep, and that's an idea. I've heard of people working on that sort of thing. I've even heard of people kind of doing a rapid iteration setup where you use Jamf4, you basically use a scanning system like lasers and stuff to scan your geometry, and then you kind of automatically import that into Jamf4 and then run it. And you're kind of in almost live, real-time, getting an understanding of your geometric space and that sort of thing. So yeah, there's a lot of room for interesting stuff like that. But again, doing absolute stuff is hard, and you're going to have to do a lot of calibration and really understand your simulation space to do something like that. Medical physics, I mentioned GATE. That's a really good starting point if you want to look at that specifically, because they are doing a lot of medical physics. They've got, radiation panels, kind of typical X-ray stuff, and then PET, things like that. So take a look at GATE. You can find it through the Geant4 website. Radiation damage. I don't believe so. Yeah, I don't think you get any sense of damage in a real way. You would have to take the Geant4 parameters that you're measuring, like energy depositions, and you'd have to do some conversion to damage in some fashion. So it would make more sense to use a code that does that specifically. So yeah, my course was offered through UT, so you had to be a registered student, but it was open to NSSC. So we had about 11 registered students and 20 auditors that were various levels of remote, as I was, and all of the materials are on GitHub, so that's free. You can just go find the lecture slides and the code examples and stuff like that. The only thing you won't have are the videos. In the future, if I do this course, I'm going to try to do it in a way that's free or trivially cheap, because I don't think this information should be gated by resources, especially for students and stuff. So hopefully in the future that's good. Yeah, there are a lot of examples for Geant4. So this is actually their main, and I don't like this personally, actually, but this is their main recommended way of learning how to use it, is they give you a bunch of examples that do different things, and they're not particularly well commented or even consistently built, right? So that between the different examples, you'll see them do the same thing different ways. And that, to me, is a little tough because it doesn't teach you an intuition for how to use their code. But there are a lot of examples, and they do technically contain all of the information you need to do what you need to do. So definitely you'll be taking a look at those. And in a lot of cases, I think people use those as a starting point. You find the example that most closely matches your use case, copy, paste, and then modify, right? And that's great. That's a very good starting point, because they've done the physics. Maybe they've done some of the input-output stuff for you. Again, it's a fast path to you doing something useful and getting a result. Automotive industry, I guess, depends on what you're doing. If you're trying to understand radiation transport in stuff, yeah, maybe. If you're doing neutron imaging of car engines or something, which I know is a thing, sure, why not? Model what you think is going to happen and then compare it to your measurements. All right, and I think this will probably be the last one because it's a little over time. I'm a beginner learning Geant4 for shielding. For gammas and neutrons for boron neutron capture therapy. I'd like to suggest some specific sources could help me accelerate my learning pace. So I haven't honestly looked through YouTube too much for Geant4 stuff. I'd be curious what's out there. For something like this, I find it's usually, especially programming in libraries, it's really hard to beat looking through a document that just says it, and you can look at the class names, you can copy paste code snippets. It's just, it's really helpful to kind of work at that level. Maybe there's some YouTube resources and some enterprising researcher has recorded how to do this stuff. And maybe when I do my course, I'll make it available on YouTube or something like that. But yeah, you'll have to look around for that. Shielding, I mentioned, you may want to use a specific physics list that is more optimized for that. I didn't go over this, but Sean talked about things like variance reduction, weights for where that's way more useful for shielding, right? There's a lot of physical pathways, geometric pathways for the particles that physically, like the probability of them happening is virtually zero. So there's no reason to actually send a particle that direction. You can do that in Geant4. There is variance reduction. There is adjoint if you want to do things backwards. That capability exists, but it's not simple to use for sure. That is advanced. I haven't used it, and it would take me some time to really get my head around how to implement that. So it's definitely a very advanced use case, but the capability is there. People use this for their calculations. So if you want to go down that rabbit hole, it's there. Go for it. All right.
Great. Well, thanks, Micah, for your time and for the lecture and for answering all those questions and for the details on your course. I'm very interested actually in the course. If you offer it again, please do let me know, and we'll make sure to advertise it if we can. So thanks again, everyone, for tuning in today. We'll see you back tomorrow for the final talk on Monte Carlo, which is about MCMP and machine learning. So we will see you all tomorrow. Thanks.